Today we shall look at the compilers which are used for generation of the machine code targeted for embedded systems and the processors which are being used in embedded systems. In fact, the compiler technology in a way is part of the design tools that are used for designing embedded systems. Because if you have to exploit the characteristics of the processor, you have to generate optimized code. And compilers provide you the tool to generate optimized code exploiting features of the target architecture. We shall look at some of the issues that compilers are concerned with in the context of embedded systems and processors which are used for embedded systems. So what are really compilers? Just to recapitulate, compilers translate high-level language program to machine instructions of target processors. And compilers obviously would need to exploit characteristics of the target processor if it has to generate optimized code. Compilation, in fact, in a way, can be considered as combination of two phases. One is your translation, the other part is optimization. In fact, we are actually more concerned with optimization because the techniques which go into the translation phase in a way are generic and not processor specific. They may be language specific, but they are not really processor specific. But when we look at optimization, and the optimization part also includes code generation, I am using it in a broader sense, includes optimized code generation, then this part is strictly processor specific. In fact, compiler determines the quality of code, optimal usage of CPU resources, memory access scheduling, as well as that of code size. You can understand that all these parameters are determinant for various functional features of the system. Because if I can use CPU resources optimally, I am not accessing memory, because one of the most important CPU resources are registers. If I am using registers optimally, I can minimize on memory access. The moment I minimize on memory access, my execution time improves. At the same time, energy consumption decreases. If my CPU consists of multiple functional units, if I can use these multiple functional units optimally, then obviously the time taken would reduce. See, if I consider a very large instruction set computer which has got multiple functional units, then the compiler would figure out the appropriate sequence of instructions so that these functional units can be optimally used. It should not be that one of the functional units is being used and others are not being exploited. The similar issue is related to the memory access scheduling. Okay? So if I can access memory in an optimal fashion, both my time and energy is optimized. This is related to the code size. If you remember the example we had considered, that if we are using ARM processor and for a particular computation, if the 16-bit instruction is good enough, then the compiler can detect that and generate maybe automatically 16-bit instructions. And we have seen that if it is generating 16-bit instructions, what does it mean? The memory required will be less, and obviously I can have the code put into a smaller sized memory in the embedded system. So therefore, compiler becomes a key resource for designing efficient software for embedded systems. Basic compilation phases, this is again a brief recapitulation. Our input is a high-level language program. Then we have these phases. The first phase, we have termed as parsing, which will also include lexical analysis. That should be followed by the semantic analysis, which is language specific, and in the process we shall also generate the symbol table, that is definition of variables, constants, functions, as well as their type information, because that type information is also used during semantic analysis. Then we can do machine independent optimizations, okay, which are not specific to the target architecture. In fact, in a way, these part of the compiler can be built independent of the target architecture. This part is machine dependent optimizations. That means it will exploit the target architecture, its features. Primarily, what does that mean? It will exploit the instruction sets, the nature of the instruction sets, and accordingly it will optimize the generated code. Optimizing generated code would actually mean selection of appropriate instructions, so that it may be that your time required for a computation would be less, because same computation can be done through combination of different instructions, and these combinations may require different number of cycles to execute. So when I am optimizing, I may like to choose a set of instructions which minimizes the number of cycles, and this would lead to time optimization. The other kind of optimizations could be in terms of memory accesses and register usages, okay, depending on the number of registers available, as well as when you have multiple functional units, the scheduling of instructions also become important. It's not necessary that you need to execute instructions in the order in which they are generated from the high level code. If there are no dependencies, in fact we have already seen such dependencies and how that such dependencies can be modeled using data flow graph. If such dependencies can be detected, and if we can rearrange instructions so that these dependencies are removed, then we can have also a better utilization of CPU resources like registers as well as functional units. So these are the different kinds of machine dependent optimizations, and you produce the machine code. Now the question could be that if I am writing program in assembly language, knowing the instruction set of the processor, you can possibly you yourself generate an optimized code. But obviously you can realize then what you are sacrificing is the portability of the code. If the architecture is changed from one version to another version, then again you need to recode the program using the features of the modified architecture. But if you are doing it in a high level language, then your entire set of applications can remain unchanged if you can really design and implement an efficient compiler. Say for example, if I am switching from ARM7 to ARM9, architecturally ARM7 and ARM9 are different. If I already have an application coded in C, and if I can use an appropriate compiler to translate your application in an optimized fashion for target ARM9 processor, then the cost that goes into recoding of the application disappears. Because compiler in a way can be used for many other applications as well. The basic principle of bringing down the cost of the design by reusing tools and modules is equally valid in this context as well. So why compilers are an issue? In fact, this point we had already touched upon. We are reviewing it again. The processor architecture for embedded systems exhibits special features, and high levels of optimization is more important than high compilation speed, because your code is expected to be compiled once and executed hundreds of times. So you are ready to pay for more complex compiler and more time in compilation. Compilers potentially help to meet and prove real-time constraints, because if it can generate optimized code, then the possibility of meeting real-time constraints becomes higher. And in fact, you can actually prove from the number of cycles required for a computation, and depending on the clock speed of the processor, whether this computation would meet certain timing constraints or not. An optimization of instruction sets of processor using retargetable compilers. This is another way of design space exploration when we are dealing with parameterized architectures. In fact, this is one point we shall discuss. If you remember, in the last class, we had talked about soft core based platforms. Okay? So that means your architecture is parameterizable. If your architecture is parameterizable, you need to now search for an appropriate instruction set as well to exploit the modified architecture. There also compiler becomes a useful tool. First, we shall look at one important issue for optimization, which is typical to embedded systems, that is energy aware compilation. Because energy is always a scarce resource, particularly for battery operated embedded systems, and you are seeing that you are getting a number of appliances which are battery operated, and at the same time providing you with sophisticated functionalities. So if I have to realize the sophisticated functionalities with minimum consumption of battery power, then compiler needs to play a critical role. So compiler can do an optimization of a machine code that reduce energy consumption. And this optimization is not that obvious. In fact, I had already talked about I can choose a set of instructions for doing a computation which consumes least number of cycles. That gives me efficiency in terms of time. But it may not give you efficiency in terms of energy. So the first kind of optimization in a way is universally valid. I would like my code to run faster even on a general purpose computer. But in this context, in the context of embedded systems, it's not that I would like my code to run faster, I would like my code to run faster consuming less power. So the optimization problem needs to look at power as well. So energy aware compilation is an important feature for embedded appliances, and in fact this interest and concern has grown of late in recent years because of availability of a number of battery powered devices. Now for such compilation, the power models form essential ingredient. What is a power model? Power model actually represents a kind of a model which encodes the energy consumption pattern of instructions of a processor. So let's take an issue example later on, we shall look at them. So here we are looking at the trade-off between optimization for low energy and optimization for high performance. High performance is available if memory bandwidth is fully used, and low energy consumption if memories are primarily at standby mode, okay, and reduced energy if more values are kept in register. So you find that if I look at this possibility, okay, then if we are keeping the variables in registers, what happens? The instructions involving registers may consume less energy. Okay, if it is consuming less energy, then it is becoming power efficient, and in a way it will consume less energy because there are no activity on the bus. Okay, so there will be power efficiency. At the same time, you are avoiding the memory access machine cycles, so that would speed up the execution as well. So if I can come up with these kind of strategies, that becomes the best for embedded systems. Now whether you can come up to these kind of strategies would depend on whether you have got an appropriate power model to characterize execution sequence for a processor. So power model actually provides you with a pattern in which energy will be consumed while execution of instructions. So let's take an example of a power model. it would provide what are called base costs and inter-instruction costs. What is a base cost? Base costs of an instruction correspond to energy consumed per instruction execution if an infinite sequence of that instruction is executed. That is, if each instruction, if you consider an instruction of a processor, and if I want to execute that instructions indefinitely, then there will be certain power consumption. So that's a base power consumption for execution of an instruction. Then there would be inter-instruction costs. What is inter-instruction cost? The inter-instruction costs model the additional energy consumed by the processor if instruction changes. Because your program will not typically consist of a single instruction. There will be change from one instruction to the other instruction, and there will be a cost involved into it. So additional cost can come because of switching functional units on and off. Because there may be, you are switching on your floating point functional unit. Okay? So that overhead, initiation of the floating point functional unit will have an overhead, and that should be modeled by inter-instruction costs. So typically a power model of a processor would consist of a base cost, okay, for instructions and inter-instruction costs. Obviously this model does not consider the memory access costs and does not attribute that to overall energy model. So we can look at another model. This model is typically keeping ARM7 in mind. ARM7 is an architecture we had all studied. Now we are looking at memory. This is data memory and instruction memory. Please note that ARM7 really does not distinguish between data memory and instruction memory because it's a von Neumann architecture. For the purpose of energy modeling, okay, when the energy model is proposed, conceptually this has been considered differently because of the reason that you will be fetching instruction from the instruction part of the memory and you will be fetching data from the data part of the memory, and there may be characteristics of the data or characteristics of the instructions which may play a role in the energy computation. Okay? And that's the reason why they have been modeled separately. In fact, the energy model that we are talking about, it has been built primarily through experimentation. It may involve simulation, it can actually involve implementation with the true hardware. Now, the different components which have been identified in this model, if you look into it, one is CPU instruction, that is the energy consumed by the CPU for execution of instruction. Energy consumed by the CPU, okay, for processing the data. Then energy consumed for memory, that is instruction fetching from memory, and the energy consumed by the data from the memory. So these are the individual components. Now next we shall look at how these individual components can be characterized, because until and unless we have these individual components properly computed and create a power model, compiler cannot use this information, because it will use this information with respect to a block of code which is a sequence of instructions, and that sequence of instructions would involve what? A memory access for instruction, then memory access for data, some computations by the ALU. So all these components have to be taken into account to find out what is the energy consumption for a block of code. So let's look at this model and how it can be done. So this is one such model. It is not necessarily that this is the universal model and the only model. So what it does is that it identifies various components for computing the cost for execution of an instruction by the CPU. Okay. So one part of it is that minimum cost CPU for the opcode I, because I am looking at an opcode I and looking at a cost of sequence of m instructions, so this summation is over m. What is the cost of execution of a single instruction, that opcode? And then the other parameters which come into the picture is, depending on that this, if you look into it, this is on immediate operands. If you are using immediate operands, if it's a registers, then register address operands. Then the question of is because register value, if we are looking at the register value, then if there is an address as part of the instruction, this is the address, and this is basically the instruction to instruction difference cost, because you are switching from one instruction to another instruction. So in fact, if you look into the whole model, this is generalization of the previous model, because you are bringing in these terms. You have brought in these terms. The previous model talked about the base cost and only the inter-instruction cost. Now you have got other terms being brought in. Now what are the significance of these other terms? If you look into it, these counts the number of ones, okay, because but it doesn't matter where the one is located, but it counts the number of ones corresponding to these operands which will be part of the instruction. And this tells you that Hamming cost, that is Hamming distance is the number of differences in the corresponding bit positions of these operands, if they are there, that is I minus 1 and I, okay. So basically from the previous one and the current one, okay. So what is the basic idea that comes up from here? We say that depending on the number of 1, because if you look into it, these are the ones which would actually float on either data or address bus, okay. These are the ones which had to be activated, okay, for execution of the instructions. They have to be put on the data or address bus, and these are the transitions which are expected to take place, okay. So this combination is the energy budget for actual memory fetch or instruction fetch, okay, because you can understand everything setting aside, that if I want to have any transactions on the bus, there has to be energy consumption, there has to be current injected in. In fact, these terms actually is modeling the activity which would take place on the bus for execution of an instruction, because execution of an instruction cannot take place without reference to operands. Operands can be immediate operands, operands can be registered operands, there can be addresses for load store operations, okay. So these terms should come in the energy model, okay. So and these alpha and beta are nothing but experimental constants, experimentally determined constants. So there are other terms, similarly other terms to come in. So here it is of the address, okay, and data address. This is corresponding to your number of this Hamming distance between the consecutive addresses. This is for the memory part, okay. So it's a minimum cost memory for instruction memory and word width. Word width will be obviously a function of this. Then memory data is if you are transferring data memory direction and word width. So again these parameters to come in. In fact, you can understand that all these parameters are also transaction based parameters, okay. So everything put together, I get therefore the energy cost, I can compute this energy cost for execution of a sequence of instructions. Because a sequence of instructions involve what? Execution of an opcode, accessing memory for data, accessing memory for instructions, computing the results, and then putting back the result onto the memory. All these aspects have been covered in this memory model. So if I provide such a memory, such a power model to the compiler, then for each block of code synthesized, compiler can compute the corresponding energy budget. So if it is computed that energy budget, what it can do? So it can do what is called energy aware scheduling. So order of instructions, take for example, the order of instructions can be changed such that the number of transitions on the instruction bus is minimized. If the transitions on the bus is minimized, then your energy cost terms decrease. Okay. If the energy cost term decrease, then that means the energy which is consumed for a block of code would be less. Fine. So that becomes the energy aware optimization. Now these can be done, the order of instructions can be changed provided you do not have dependencies. So it might require application of standard compiler optimization techniques. We have seen one such technique of variable renaming earlier. Okay. So I can do a variable renaming, remove the dependencies, then reorder the instructions to find out a combination of instructions which minimizes the energy consumption. So this becomes energy aware scheduling of instructions by the compiler. The other thing could be the energy aware instruction selection. Instead of looking at just at the number of cycles, it would look at the combination again, which would minimize the energy consumption. In fact, if you see, this becomes also part of design space exploration. What are you exploring? Different possible ordering of the instructions. And in a way, this exploration can be done with reference to each hardware unit that you are using in a embedded system. Okay. The other kind of things which are common is operator strength reduction, replace star by plus and shift operations. Obviously, here the logic operations for a multiplication would involve a more complex logic circuits, and if we can avoid that by using simply ALU and barrel shifter on ARM, I shall be getting much better energy consumption profile. And there can be standard compiler optimizations also are used with energy as a cost function. Now let us take an example of this. Let us consider this code. If we look at this code, this is simply a array access, and I am doing a computation involving array access and taking the value in C. There can be any kind of computation. This computation example that we have chosen is in a way random. Now, if we can do an appropriate register allocation, okay, then we can reduce energy consumption substantially, because both these array accesses are memory intensive. Any array access would means activity on the bus, and you have seen the activity on the bus contributes to the energy cost. Okay. So activity on the bus would be there if I am accessing these arrays. Question is, how do we minimize this access? Now, if for minimizing the access I need to allocate registers, let's consider that we are having registers R1, R2, just like ARM kind of a scenario where I refer to registers by Ri. We can consider that scenario. Now here I am showing you one possibility where A0 is assigned to R2, okay, and what we are doing, I am assigning AI, okay, because this is 0 to 10, AI to R1. So R2 is actually containing AI minus 1, fine, and then I go through this loop. So this computation is same as that of this computation, but here for each computation what I have got? I have got two array accesses, the way the code has been written, but here I have reduced it to a single array access, and I am doing the computation here involving simply these registers R1 and R2. In fact, a very standard compiler optimization would possibly do this as well, because I am saving on time also, but at the same time I am saving on energy. So energy aware compilation becomes very important for battery powered devices. Now these kind of instruction choices can save energy to a certain extent, but it has been found that the major saving on the energy can be really done if we reconsider the memory architecture, because you have seen from all these models, memory access becomes a critical component. In fact, some smaller memories provide faster access and consume less energy per access. And substantial saving is possible if compilers can exploit existence of what are called scratch pad memories. In fact, we had discussed scratch pad memories when we looked at the memory organization. So what are really scratch pad memories? Scratch pad memories are high speed on chip memory. Okay. What is the difference with cache memory? Cache memory really are not part of an address space. It's mapped from the main memory to cache, but scratch pad memory is part of the address space. Okay. And it is on chip and fast. So if you look into it, what we are looking at is a processor, and I have got SPM. This can be cache memory, and this is the main memory which gets mapped onto cache, and this SPM is part of the address space. And that's why I'm referring this as no tag memory, because if it's a cache, then it has to be tagged. Now, how do we exploit SPM? Because if I have SPM, I need to exploit it. I can exploit it if compiler knows how to exploit it. So the compiler has to be now made conscious about existence of scratch pad memory. Now, how can compiler exploit scratch pad memory? Your program would consist of various blocks. There can be for loop, while loop, repeat, call, data structures, there can be arrays. The question is, compiler has to take a decision about putting which of these blocks, code blocks as well as data blocks, or either code block or data block, into the SPM which has got a fixed capacity, so that your execution speed is maximized. That means the time taken for execution of the code is minimized. So I cannot put blindly the things onto SPM. It is not like a cache. Please keep in mind, the problem is different. Okay? In case of a cache, when you make an access, okay, then that memory gets mapped onto cache, and you try to organize the data and instruction in such a way that cache hit is maximized. In fact, we had discussed this point earlier. Now what we are looking at SPM. If you are looking at SPM, one possibility is a static allocation. That means the compiler decides at the compile time itself to allocate these blocks onto SPM. So they will be on the SPM always. Okay. In a cache, it's not a static allocation. Cache is typically a dynamic allocation depending on demand. So how this problem can be solved? So we can identify each basic block, and each variable can be modeled as a memory segment I. So basically compiler is dealing with a set of memory segments. And for each segment, there is a corresponding size, Si, okay. And we can compute gain Gi of moving segment I to scratch pad memory, okay. Because what is the gain? Gain would come from if that block I is in the main memory, what is the time taken, and what will be the gain if I move that from main memory to a scratch pad memory. Now this gain can be estimated using profilers, okay. We have talked about profilers which can give you the estimate of code segments in your program. So using profiler, you can figure out what could be the possible gain of moving a segment I to scratch pad memory, okay. After that, the problem becomes a optimization problem, because what you would like? You would like to optimally exploit the SPM area, to maximize the gain. So it is a pure optimization problem, just like a hardware software partitioning problem. In fact, this is a partitioning problem in the sense that you have got the code and you are trying to partition the code between main memory and SPM. So a formal representation could be in this form, where we are looking at simply migration of functions. We may not look at each variable, but we are looking at, say, simple migration of functions. So size, each function would have a fixed size. This is size of the function. Ni is the number of instruction executions in the function I. Ei is the energy saved per instruction execution if Fi is migrated, okay, and it can be really independent of I, Okay. EFI is energy saved if function Fi is migrated. So, it can be computed by multiplying EI and NI. K is the size of the scratch pad memory, and MFI is a decision variable. Okay. If function is migrated to SPM, L0. So, I have got effectively a 1-0 optimization problem, 1-0 integer programming problem, because I am trying to do what? I am trying to maximize this gain. Okay. This gain is EFI. EFI has to be multiplied by the decision variable and sum it up. So, I shall be getting that as a total gain, and I want to get that gain, okay, subject to the constraint that SFI, this is the size of function I, multiplied by the decision variable is less than K, which is the size of a scratch pad. So, this becomes an integer programming problem. So, compiler should have this kind of an optimization routine to figure out what are the functions which are to be migrated to scratch pad memory if it is required. Okay. So, effectively we shall allocate the blocks. Okay. So, in fact, this is a block BB1 and block BB2 which gets allocated to your scratch pad memory, and your main code is in the main memory. So, effectively you have to introduce jump instructions, and what we say is that fine grained granularity smoothens dependency on the size of the scratch pad, requires additional jump instructions to return to main memory. And in fact, why fine grained granularity smoothens dependency on the size of the scratch pad? Because then if the granularity is small of the units that you are considering, then you can migrate them smoothly. If there is small increase in the scratch pad, then one more granule can move in. So, the efficiency increases in a smooth fashion, and obviously you would require these additional jump instructions, and in fact there could be an interesting optimization with respect to this also, because if there are consecutive blocks mapped, then these jump instructions can be actually removed. Otherwise, the basic framework is your main code is in the main memory, introduce jump instructions, migrate part of the code to your SPM, and again put a jump instruction at the end of the code to go back to the main memory. In a way, you are violating the principles of structured programming, but you are violating to exploit the memory characteristics. In fact, exploiting this scratch pad memory energy behavior. In fact, it is found that use of scratch pad memory, and by optimally mapping the blocks to scratch pad memory, you can have substantial energy saving. In fact, many of these cell phone based appliances where they have the GSM coder and GSM coder implementations, benchmarks have actually shown that migrating the code onto scratch pad actually enhances battery life substantially. Now, other possibility could be dynamic replacement within scratch pad. Okay. So, the basic idea is that address assignment within SPM is required. So, something like paging or segmentation like. So, the basic idea is this is the code, and I can have these are the pages of the code, logical pages or the segments of the code, and these segments are moved to SPM depending on the requirements. Okay. And so, effectively results in a kind of compiler control segmentation or paging for SPM. So, here the OS is not really coming into the picture, but compiler is coming into the picture, because compiler is mapping the different components of your code which is in the memory to SPM depending on the requirements. Now, why this should be a desirable strategy? Because if you remember, the locality of reference is a temporal phenomenon. Okay? That means I might be executing a function a number of times over a certain period in the program. At some other point in the program, I might be executing some other function, and it may not be possible for me to accommodate both the functions in SPM. Okay? Because SPM also involves cost. I cannot have everything SPM because SPM involves cost. So, I would like therefore a function which is currently being used heavily being mapped onto SPM, okay, and later on the other part of the function will get mapped onto SPM when that function is being used in my code. In fact, extending this idea would be if you have a multitasking model, multi-process model with the OS, then how the multiple processes have to be accommodated on the SPM. Because accommodation of multiple processes then becomes a problem of OS, okay, and under those circumstances you have to see what is the SPM budget that you are allocating to a compiler if I am statically doing an allocation in a process specific fashion. So you can see I have again changed, so one has been overwritten, the reference I was making to temporal locality, that it is now then this part which is currently in SPM for execution. Next we shall talk about other architecture specific adaptations. These architecture specific adaptation refers to processor architecture. Compiler needs to take advantage of the architectural features of the processor, okay. So it can be for DSP, because DSP instruction set and architecture is different. There can be ASIPs, ASIPs are application specific instruction set processor, and parameterizable processors normally does not have support of good compilers. Now this is a very big problem when you are talking about a platform based design, because if you are parameterizing a processor, how can you have a compiler which is efficient and had put in all these optimizations so that you can translate your high level language code to the target architecture. So design space exploration actually can involve designing of the processor along with the compiler with selection of instruction set, okay, so that finally you get an optimized implementation. So here the issues are architectural retargetability, compilation tool to adapt to different processor architecture. So we have talked about so far compilers tuned for a particular architecture, okay. Now we are talking about whether I can have compiler retargeted for various architectures. In fact, that is more feasible if I have a compiler targeted for a family, but now I parameterize on various features of that family. So in that case, can I have a compiler generated for a parameterized processor? Because the moment I am parameterizing processor, I have also the flexibility to choose its instruction set, okay, and accordingly the compiler should get automatically modified to generate the code, because using that you can explore the design space. The code quality is obviously compiled solution to exploit all the architecture features of DSP or ASIP architecture would be low cycle count, low instruction count, and you would like to optimize these along with the energy as well. Let us take an example of these configurable and reconfigurable processors, because this is exactly the point we had discussed earlier also. If I have a configurable processor, the CPU architectural features are selected at design time. Reconfigurable means hardware can be reconfigured in the field and may be dynamically reconfigured during execution. Now in that case, what kind of instructions do you generate? What kind of instructions the compiler should generate to be optimal with respect to the architecture which can undergo modifications? This is actually an open and a serious problem. We shall obviously not look at this problem in its complete complexity. We shall just briefly touch upon its different aspects. We are looking at an example, say 10 silica configurable processors. So you can actually configure the processor parameters. This is again an example of a soft core kind of a scenario, okay. So effectively what you get, you can configure processor parameters. As you configure processor parameters, you can also design the instructions for the processor. Now you get a result is HDL model for processor, hardware description language model, which can be in VHDL, and you need actually a software development environment. If you do not have a software development environment, you really do not know what to do with configured processor, okay. If you see, we have studied the design of embedded systems. Design of embedded systems is what? Not just designing the hardware. If you are coming with a task, we need to map software to hardware, okay, hardware blocks if required, tasks to be mapped to hardware blocks, develop the software for it, So I need a complete environment to evaluate a processor and do a design space exploration to select a platform instance. Related to this is a concept of application specific instruction processors. ASIP is a stored memory CPU whose architecture is tailored for a particular set of applications. In fact, the current trend is go for ASIP rather than ASIC, okay, because then ASIP gives you a kind of a flexibility so that it can be used for a number of applications exploiting the similar characteristics instead of just designing an ASIC targeted for one specific function. So the programmability allows changes to implementation using several different products and high data path utilization. In fact, this is a basic reason for going for ASIPs. An application specific architecture provides smaller silicon area, higher speed. So enhancements are performance and cost enhancements, special purpose registers and buses to provide the required computations without unnecessary generality, special purpose function units to perform long operations in fewer cycles, and special purpose control for instruction to execute common combinations in fewer cycles. Now all these are features of ASIPs. Now, and these ASIPs can be actually designed in an application specific fashion. So the problem that comes up is what is called ASIP co-synthesis problem. So you are synthesizing a processor. So given a set of characteristic applications and required execution profile, you would like to automatically generate microarchitecture for ASIP core and optimizing compiler targeted to the synthesized ASIP. Okay? So you are not just designing now the architecture, you are also designing the compiler, because if you do not have the compiler, you cannot really have your task executed on the target processor in an optimized fashion. So your co-synthesis problem is that of designing the architecture as well as designing the compiler. So implement application using core and compiler. So processor synthesis, choose an instruction set, optimize the data path, extract the instruction set from register transfer design, and compiler design, drive compilation from parametric description of data path and instruction set, bind values to registers, select instructions for code, match to parameterized architecture, and schedule instructions. Now you will find various part of it. If you look at bind values to registers, select instructions for code, match to parameterized architecture, schedule instructions. If you remove the parameterized part of the architecture, these are the job which are done by the compiler as it is. But your standard compiler doesn't work with the specification of a processor. You already know the processor, and then you have built in the algorithms in the compiler to do the optimization. Now here, for the compiler, you need an additional input. That is the description of the architecture itself. Okay? So the key technology in this case is retargetable compilers. So what is a retargetable compiler? It is a compiler which is just not a language specific compiler, but it is based upon architectural model. It generates code for the class of processor architectures that fit its model. Okay? Because even when you are generating an ASIP, in fact ASIP you can generate from any of these soft code models, that means you have got a parameterized family in many of the cases. So you are not changing the architecture per se, but you are playing with some parameters, some features of the architecture, keeping basic family unchanged. So there are various ways to classify parameters for processor architecture. It can be an arithmetic specialization, that is whether you are using a real or a floating or integer or fixed point. Data type being used, then code type. Now code type can be two kinds, in fact data stationary or time stationary. Every instruction controls a set of operations that have to be executed on a data item as it traverses the data pipeline. So this is called data stationary code type architecture. Time stationary is every instruction controls a complete set of operations that have to be executed in a single machine cycle. Now please try to understand the difference between the two. Data stationary is every instruction controls a set of operations that have to be executed on a data item as it traverses a data pipeline. Okay, so there is a data pipeline, the data traverses, and you are talking about the the set of operations to be executed on the data path. Time stationaries controls a complete set of operations that have to be executed in a single machine cycle. If you consider a VLIW kind of a processor where there are multiple functional units, then I can schedule operations on each functional unit, and that can work on different data. Okay, so you have got a time stationary model vis-a-vis a data stationary model in terms of architectural features. There are other classification parameters as well, say memory structure, von Neumann or Harvard, operand location, whether it's your register operations or memory or memory register structure. If it's a RISC kind of a thing, it will be homogeneous. If it's a CISC, then it will be heterogeneous. Addressing modes, control flow, because there can be standard control flow, or if you are bringing in some of the DSP features, you may have zero overhead loop as a control flow feature in the architecture itself. Okay? And so there need not be separate cycles for loop control. Also, there will be residually control, in the sense operation depends upon bit values in a control register. Say for example, with ARM, if you set the thumb bit, the instructions or operations are 16-bit. So then with these features, you get this model of retargetable compilation. So this is a simple C code. This is an application code which goes through front end. Your code generation makes use of the microarchitectural model. That architectural model can be in hardware description language or various other languages which are used for describing high-level architecture as well as the instruction set. And then you generate the code, because see, this instruction set definition also comes from here. So you make use of the instruction set definition, look at the microarchitectural model, and then look at the object code. Now, if you are actually doing a design space exploration, it means that you have the object code, execute the object code, get the performance estimates, go back, modify the microarchitectural model, okay, modify the code generation, again try it out. Okay. So if you are actually doing this kind of a soft core based development or a platform based development, this is one way to do design space exploration. The point I was making, that compilers are also tools for design space exploration. In fact, it's a design tool for embedded system. So there are various ways you can specify the processor. There can be typically net-based language. So netlist-based languages gives you a structural model. There can be high-level languages which can describe processors in terms of structural skeletons, data types, storage elements, and description of actual instruction set. Then there are template pattern bases, essentially enumerates different partial instructions available in instruction set and often expressed using a grammar. So by modifying these rules, you can generate other instructions. Also, there can be graphical models. So you can have connection operation graph, place time graph, which permits you how the legal data moves, also the instruction set graph. In fact, we can see that if I have an instruction set graph, what does that mean? If it's a plus operation, this is a simple instruction set graph. This is minus, this is a multiplication. And this is the expression tree which is generated through your code generation and semantic analysis. So your code generation would therefore mean mapping of these onto these instruction graph. And in fact, you can modify the instructions by changing the graphs. Okay? And there could be various ways of describing the instructions. So just keep in mind that if I'm specifying the processor, okay, I can design a processor, I can get a hardware description language which describes a microarchitectural model. From there, I can derive the instruction set, I can describe instruction set in various ways, and the compiler makes use of the microarchitectural model as well as the instruction set to generate optimized code. Now, in fact, the tree covering, a very simple algorithm, is that of generating code is in this way. Because these instructions, so I have covered this with one operator. Then I choose what is the next operator I can make use of. So I get this next part covered. So that means this could be a register operand which has to be replaced here. So that's how I can generate now instructions given a graphical model of set of instructions giving a graphical model. In fact, this algorithm is used for general instruction selection as well, can be used for general, it is actually used for general instruction selection, but in that case these models are provided right at the beginning, they are not input to the compilation phase. For retargetable compilers, they are input during compilation phase itself. So we see what are the uses of retargetable compilers. Retargetable compilers help in the design space exploration phase of application design process while tuning an initial architecture towards a given application. Okay, because I can modify the architecture, modify the instruction set, generate instruction set absolutely tuned for my application if I have this kind of parameterizable features. Retargetable compilers in combination with maybe assemblers and simulator provides feedback to the designer about architecture efficiency with respect to a given application. And retargetable compiler may serve as a starting point for production compiler once the architecture is fixed. That means when you are designing the architecture. This is not for configurable or reconfigurable platforms. This is a design process of a processor itself. So in a way, retargetable compiler is an interesting design tool for embedded system designers if you are trying to design an embedded appliance on a configurable system or using some kind of a platform which gives you the feature to modify the hardware architecture. So today we have looked at some of these compiler related issues, and we have understood that efficient compilation forms the basis for useful design of embedded systems. Any questions?